Professor Samir Shende. So he serves as the research professor and the director of the Performance Research Lab at the University of Oregon and the president and director of ParaTools. He serves as the lead developer of the extreme scale scientific software stack, or called E4S, Tau Performance System, Program Database Toolkit, and HPC Linux. His research interests include scientific software stacks, performance instrumentation, compiler optimizations, measurement and analysis tool for HPC. He served as the general co-chair for ICPP 2021 and is serving as the general co-chair for Europar 24, which will be taking place next week. He was the vice chair for the technical papers for SC 2022 and has served as the chair of the performance measurement, modeling and tool tracks for the SC 17 conference. And he received his BTech from IIT Bombay and his master's and PhD from University of Oregon. So today you will be going into a lot of hands-on, very interesting things. Samir will introduce ParaTools Pro for E4S, a development environment for HPC and AI ML applications. So let's give a big welcome to Samir.
Thank you very much, Dikshit, for inviting me here. So today I will have a hands-on session as part of our ParaTools Pro for E4S talk, and feel free to ask questions and try out these tools. So we'll all log in. This is the only URL you should look at, this tinyurl.com/E4S-tut for getting set up. I hope you can all access this. Reserve an instance. We have spun up 4 clusters on AWS with NVIDIA GPUs, and we have 1 cluster on Google Cloud as well with NVIDIA GPUs as well. So these clusters have a login node and a couple of compute nodes, and you will use them pretty much like you use your HPC resources. Just a show of hands here, who has used cloud systems in the past? Was it painful? Fairly? Okay. So we'll see how your experience compares with what we have set up for you. The key motivation for this is that as our software is getting more and more complex, it's getting harder to install all our tools in a consistent manner to assemble a software stack that is usable. We have many libraries, applications, and the dependency tree is just exploding. It's reached such a crisis point that, as you know, many supercomputing centers are hiring multiple FTEs just to build our applications and run them on these systems. So we are taking a step to reduce the complexity of the software stack and how you can make it more accessible to the users. And also it's getting harder to measure the performance of our HPC and AI/ML workloads. So we'll look at both of those problems in this, and I would like to present the extreme scale scientific software stack. This is a project from the Department of Energy. It aims to deliver a modular, interoperable, and deployable software stack. Our goal is to improve the access, lower the barriers for entry into HPC and AI/ML tools, and our software stack includes the Tau Performance System, another project that I have been working on. And this is used for measuring and optimizing our workloads. We have a E4S ported to commercial cloud platforms using this ParaTools Pro for E4S image, which we'll use. Here's the URL for the project. And the Extreme Scale Scientific Software Stack, or E4S, is a community effort. It's a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. E4S provides a curated SPAC-based distribution of over 100 different HPC tools and libraries. SPAC is the package manager that we use. Both E4S and SPAC are part of the Linux Foundation, and they are part of the High Performance Software Foundation, or HPSF.io, which has been recently formed. These packages include applications that you may be using already, such as OpenFOAM, GrowMax, NEC 5000, LAMPS, EDA tools like Zeiss, AI/ML packages like TensorFlow, PyTorch, TorchBraid, and other packages that are over here. We have a distribution that can be used on bare metal platforms, in containerized deployments, and on cloud systems. The goal is you should be able to use this software stack on your laptops, on your departmental clusters, on your supercomputers, and on cloud systems, and provide the same consistent environment, which is based on SPAC and other tools. And we support x86-64, the IBM Power platform, including Power 10, Power 9, ARch64, ARM64, with support for GPUs where available from NVIDIA, AMD, and Intel. And all of these tools are built for these GPU platforms. Those of you who may be using AI/ML frameworks may know how difficult it is to make sure that your say PyTorch installation is actually using the GPU correctly and not the CPU. So those questions can be very easily answered with using pre-built packages from E4S. These container images are available on Docker Hub as well as the E4S website. There is commercial support provided for E4S through ParaTools Inc. We have a partnership with Adaptive Computing. They provide the on-demand data center product which is used to launch the images, including ParaTools Pro for E4S. And it supports AWS and other cloud platforms as well, including Google, Azure, and Oracle. We have some tools like E4S chainspac.sh to chain the two SPAC installations, one in your home directory where you can install new tools, chained to the read-only file system based installation that your system administrator may have deployed or in a container. We have a tool to substitute an MPI in your containerized application with the system MPI. You may be using, say, an HPE Cray system, and you may have a Cray MPitch over there, or you may have MVAPitch installed with InfiniBand on your cluster, and you can substitute the MPI in your containerized E4S application with the MVAPitch running efficiently on the InfiniBand, so you can get the best performance. We also have a tool called E4S ALC, or a la carte, that can allow you to pick container image that E4S provides and add more packages that you need to create a custom container for you. So it's an a la carte selection tool. The idea is that we don't want to create a software stack that we can claim meets 100% of your needs. We want to reach the 95% mark. We want to make it so that most of the dependencies that you normally need are already available in this distribution. You can tweak and install the remaining 5% to make it the perfect distribution that you need. So with containers, just a recap, it contains everything that you need to deploy your application minus the OS kernel. It uses the OS kernel from the host. You may have seen hypervisors in the past where a hypervisor is directly over the hardware or over an operating system which launches a virtual machine, maybe using VirtualBox, where there's a full operating system with the overhead of a separate kernel. So there is a kernel running on your host and there is a kernel running in the VM. That second kernel is no longer necessary when you use containers. It uses the kernel of the host. And these are all the libraries provided in a separate OS distribution that runs on top of your host. And we have just had a release this summer, and E4S 2405 includes 129 HPC packages on these different platforms. We have binaries in the binary caches so that you don't have to recompile all the packages from a scratch. We have a new integrated development environment called Codium those who have used Visual Studio will recognize that this is the same environment. Of course, it's with an MIT license. We have a doc portal update. We have a new operating system for the containers. We have upgraded CUDA. There are new tools. And we have some new applications, including NEC 5000, Neckbone, Lagos, and previously supported packages like GROMACS, CP2K, Zeiss, Quantum Espresso, Exago, LAMPS, WarpX, DL2, OpenFOAM, and support with ODDC that we will use. So here are some of our releases starting in October 2018, where we had 24 products. Now we are up to 129, and it has a collection of HPC as well as AI/ML packages. You can go to E4S.io to download the containers, and you can see the releases for these containers, such as this one with the CUDA. We have Docker and Singularity with support for different GPU platforms. You can have a full-featured GPU image, which you can use with Docker pull, or you can just use a base image. The difference being a full-featured image has all these 129 packages. A base image has the vendor runtime. So CUDA, ROCm, Intel 1 API, maybe CMake and the MPI, but nothing else. You can install with SPAC all the remaining packages that you need. And we also have a minimal SPAC-based image which has MPI and the compilers, but no vendor runtimes for CPU-only executions. Here is the E4S ALC tool. It's the a la carte selection tool. You can basically say, take this base image, add these 5 packages from SPAC, these 2 packages from the system manager like Yum or Zipper, and then just create a new container for me. Please don't ask me to write a Docker file or a Singularity definition file. It takes care of all that. It just creates a container for you. You can even expand a tarball and say, install this in this directory. There are other LLVM images, continuous integration images. There's a lot of CI that's going on behind the scenes. So, and we also have these facility deployment images. Yes,
so,
go ahead.
This is fantastic. So, is the scripts or the backend to create all of these, let's say, images available for others as well? Let's say if I want to create Docker images for MVAPH Plus, yes. Would we be able to reuse some of these scripts?
Absolutely, yes.
Okay.
Everything is documented in the documentation section, okay. And you can check that.
Okay, and with most library, for instance, I'm assuming that E4S has a lot of MPI libraries. So they would have dependencies on CUDA or ROCm or all of those drivers. So does the scripts handle all of the, for instance, if I want to create a RPM for CUDA 11, CUDA 12, ROCm 6, ROCm 5, are all of those handled?
So here? We have, for a given release, a specific version of CUDA that we are doing. So we are not, in the default installation, it's not all of those, but we include NV HPC.
Okay.
NV HPC's latest version has support for some, not all, CUDA releases. So they'll have like a CUDA 11 release, they'll have a CUDA 12 selected version. So the latest version of NVHPC or one API is available over here.
Okay.
And you can customize it starting from a base image where nothing else is installed.
Okay.
And then take a E4S ALC and say, add all of these packages in SPAC using, for example, MVAPH is one of the installations and all the others. And it will create the Docker file for you. And then you can tweak that Docker file if you want, and then create a container from there.
Okay, so for instance, if I want to create Docker images with MVAPH Plus supporting CUDA 12, 11, 10, then I could use the like ALC software that you mentioned
exactly.
to create the Docker images.
You could start with a base image,
okay.
add more packages, create a custom container,
okay.
and then customize it. The whole idea is that we should provide all the tools to create a custom image for you.
Okay, okay, thank you.
And we have facility deployment. Here are all the documentation files for installing it on bare metal. If you have a HPC platform, you can use these recipes and then install it. We have a product catalog, and these are not static pages. Every night, our scripts, rake the info from the GitHub repos and populates this. So you get the most current information from this. You can look at the Docker Hub directly for some of the containers that we have. You can see what that contains and then tweak it as you would like. Here are the releases for base images. You may want to start with some base images, see the vendor runtime in there and nothing else, and then create the whole stack as you need. And then there is the ROCm release, there is the One API release, and yes, we have the ability to redistribute Intel base kit and Intel HPC toolkit. This allows us to redistribute Intel compilers under a special licensing agreement with Intel. You have to, of course, agree to the end user licensing agreement when you use any Intel product.
As an end user, so typically, at least in the past, it was very hard to get Intel compilers.
Intel compilers?
Yeah.
Yes,
so
impossible.
Now with this, would I be able to get Intel compilers, let's say, with this particular Docker image? Is that what you're saying?
So we have base images as well as full-featured images with Intel compilers.
Okay.
Yes. I can offline discuss licensing questions with you.
Okay, thanks.
And here are the packages, in case you are wondering, what are these 129 packages that we have? These are packages that you already know and may be using. Packages like Adios to Ambrex. You may be already using packages like Dynast API, GasNet, or HDF5. You may be using packages like Magma, or LAMPS, or Hyper, or Cocos, or OpenMPI, or PAPI, or ParaView, or ParallelNet CDF, or Sundials, Raja, Tau, Trilinos, PETC. Many of these packages that are very widely used in HPC that are available over here, and we can chain two SPAC instances. For example, I can create in my own directory a temp SPAC directory, and I can just say chain the current SPAC with this new directory. It will clone it, it will connect these two so that I can just transparently install tools. Now with the web-based image that you will be using, this has already been done. So anyone can just say SPAC install, say Valgrind, if Valgrind is not installed, and it will just install it and put it in such a way that you can see a union of both of the packages that are already installed as well as the packages that you currently installed in your directory. So each user can customize this. Here is a Python example which uses TensorFlow, PyTorch, and you can see this is running on the latest NVIDIA Grace Hopper GPUs. If you are looking at Python tools, please have a look at this list. It includes OpenAI, Gemini, TensorFlow, PyTorch, JAX, TorchBraid, DeepHyper, Pandas, CV2, Scikit-learn, as well as other tools like Open3D, NumPy, SciPy, Matplot, Plotly, Seabone, MPI for PY. So when you are using this on the AWS instance, you will see that MPI for PY is connected to MVAPitch, and you are able to launch those workflows with MPI, getting the best performance between the nodes as well as within the node. And you can see all the other packages for GPUs. We have this package that allows you to specify which MPI to use and substitute the MPI in the containerized application with the system MPI, such as MVAPitch on our AWS system. All you need to say is, which is the runtime, like Singularity, where is the Singularity image located, and what do I do to bootstrap the container, like set up the SPAC and SPAC load a package, and then you can just say E4S CL MPI run and your application with the flags, and it will substitute this. What this is trying to do is enable you to distribute your applications in a binary form. Until now, you were only distributing your applications as a source tarball. Now you can distribute it with the E4S container in a binary and go to a platform, say your departmental cluster where MVAP is already installed, and substitute the MPI embedded in your application binary with the system MPI, with no change to the binary. There are some community policies in E4S. It uses SPAC. SPAC is a mature package manager. You can see that the red boxes at the top are the packages about 100, and the blue boxes over here are all the dependencies that you need to build it. It's a very complex process. And we reuse these dependencies, as you can see over here. So we make a complete software stack with all of these packages. And this is how you can get started with SPAC. You can do a source for the SPAC setup environment. You can find the compilers and other packages. Then you can install a tool like Tau. You can say SPAC install Tau, version 233.2, using GCC compiler, version 11.2.0, with MPI, Python, pthreads, these variants in the package recipe, using MPI from MVAP version 2.3, for example. And it's used to build a whole lot of other software, and you'll find that SPAC is growing in popularity. It has over 8,000 packages now. It's widely deployed across different computing centers. And our image for the cloud platforms takes E4S and makes it available on cloud platforms. In case you are deploying to the cloud, you are probably wondering, which cloud platform should I use? Should I use AWS? Should I use Google? Should I use Oracle? Should I use Azure? Why not all of them? How can I use a single image that will work across all of them? How can I launch those images easily on all of those platforms? You already struggle with connecting to one cloud provider. Those who have used it, you know that experience was not something you will forget, right? It was pretty bad. How can you make it easy? And today we are going to log into the cloud platforms within a minute without installing a single package on your computers. There is no GHPC, there is no Azure command line tools, there is no AWS parallel cluster or Oracle cloud infrastructure command line tools to install. Everything is web-based. Okay. HPC and AI ML workloads need low latency, high bandwidth. You may be wondering which MPI to use. Well, maybe not here, but which image do you want to use? And how do I provision and build the image on different cloud providers? How can I burst to the cloud from on-prem clusters using batch submission scripts? So there are multiple MPI providers. We use the most performant MPI for cloud platforms, which is MVAP, interfacing with the job scheduling packages. There is Moab, Torque, Slurm. MPI must interface with that scheduler package. The cloud providers have different inter-node network adapters like EFA, InfiniBand, Mellanox, IPUs on Google Cloud. You need to make sure that you are using the most efficient communication library for intra-node as well as inter-node. Within the node, you want to use XPMEM drivers. This requires a kernel level module, right? So you use very efficient communication within the node. GPU direct async support is important for GPUs. We are building E4S optimized with MVAP for all of these cloud platforms and using the ODDC interface to launch this image. And it looks like this. The user interacts with the ODDC front end, and then you can target multiple cloud providers. ODDC is a commercial product that comes from Adaptive Computing Inc. And you have the listing of ParaTools Pro for E4S, the image on AWS Marketplace. So we'll jump right in, and all of us online as well as participants here should go and reserve an instance. How do we do that? We go to this first URL, tinyurl.com/E4S-tut. The slides for my talk are over here, and whatever I do is in the slides, step-by-step instructions. So please go and reserve an instance. And then once you have reserved, this link is also in the web page, go to this paratools.adaptivecomputing.com, maybe use Firefox, and then log in with the tutorial number. For example, if I chose an ID like tutorial 07, and I see the password on the web page, please go and use that login and password to authenticate. And please let me know if you have any issues in access. You will probably need to tell Firefox to allow pop-ups, and you click the allow pop-ups from this paratools.adaptivecomputing.com, and then you just click that image like this. You will see these clusters. You click that link over there, and then you should see the configuration tab with the cluster information. You just click the Open VNC Viewer and accept the pop-ups for ParaTools Pro. You will get a screen like this. You click the Connect button, give the same login ID that you picked. So I've got 4 clusters. I've tried to put like 15 people on each of those. And I actually, there is room for 20 on each of those clusters. And I also have another cluster on Google Cloud, which is going from tutorial 81 to 100. So you can actually just pick one of the AWS, one of the Google if you want to try both of them. But AWS cluster has EFA, Google has IPU, but the same environment is there on both of them. And then once you get this screen, this is a remote desktop. You have a remote desktop to a cluster. You click over here, these 9 dots. You click on the terminal icon over there, or you can search for the terminal. Then you will get a terminal, and then it will take a minute or two to expand the SPAC in your home directory. It will set up examples over there that we will use. So the first time it takes a minute or two for it to expand. So just be patient. In the meantime, you can just right-click, go to the preferences, go to the custom font, and then change the size of the font maybe, so it's a little bigger, easier to read. And then you can just go to the example, start with an MPI proc name, compile it, and submit it just like you would with any cluster. Say qsub, and run the submission script. You can check the status of completion on those 2 nodes with qstat-u $user and see the output file in MPI procname.o. Maybe you can also go into the OSU benchmarks directory and run the bandwidth benchmark. See how close you get to the EFA limit. For this instance, we have a EFA adapter that is rated at 50 Gbps. So how close can I get to 50? And we are using MVAPITch for the most efficient communication between these nodes. So you can see how we are running this, and let's try this hands-on, all of us. So if you have been able to log in using this, please raise your hand. So you are all logged in, right? The others, please go to this E4S-tut and just reserve the instance name, and then go here with the login and password. Now, those who have been able to log in, compare this with the experience you had previously of connecting and setting up a cluster on a cloud provider. Okay, a shared cluster with multiple users, with multiple remote desktops running simultaneously, with shared access to a GPU resource where the login node has a GPU. So you can say NVIDIA SMI, for example, and the compute nodes have GPUs.
So I went ahead and I was trying to run Nemo. Any idea how long it would take? It says star file X is finished conversion and it's kind of waiting there.
Pardon, did you say you want to run Nemo?
Yeah.
So you can go to examples, Nemo,
Okay.
go to CD EX1, for example, and just say /run.sh.
Okay. Okay.
There's a run.sh over there. If you want to run it on multiple nodes, you can go to EX2.
Okay.
That takes a little longer.
Okay.
So, but you can run it with QSub so that
Okay.
there's a distributed processing. But
Okay.
try running EX1
Okay.
with run.sh, even with Jupyter notebooks. Are more people able to access this now? Are you still having problems in connecting?
So I tried to run the top level run.sh. So
EX1?
Yeah, no, there was a run.sh at the top level.
No, don't run that.
Okay.
Do not run that. Just go to EX1 and then run it as /run.sh.
Okay.
And it has a WAV file, WAV file, which says something like GLENN or something, and it will transcribe the contents of that.
Okay. Okay. Thank you.
So yes, it does have a lot of AI/ML packages in there. Let me try running over here. Here is my desktop. And I'm connecting here. Do you see a screen like this with the terminal window? Like this. I'm going to go to examples directory, mpi-proc name. I'll do a compile.sh over here. And then here is a mpi proc name .qsub. This is my mpi proc name .c file. So you can see what I'm trying to do over here. I have an MPI in it, MPI com size, MPI rank, MPI finalize. I'm just saying print I'm this rank out of that rank. The first thing you should do whenever you go to another cloud system is don't believe that MPI works with their scheduler. Okay? Don't believe that you are going to actually get this until you run a program like this that shows you that you got the correct MPI com world and that your ranks go from 0 to n-1, that the connection between MPI and the scheduler is working. So what I'm going to do is I'm going to specify over here. You see, I'm not even showing MPI run with the number of processors. I have specified this in the PBS. Nodes equals 2, processes per nodes equals 2. Okay? So when I say qsub and say mpi proc name .qsub, it has submitted the job, and then I can just say qstat -u $user. This will show me that the job just completed. Oh, how nice. Okay. Now, a faulty MPI connection with the scheduler will launch something that says 0 of 1 4 times. And the correct one will say what? 0 going through 3 with the out of 4. So if I show this output MPI proc name .o, I can see that it is correctly running on 2 nodes over here, on 2 nodes over here. The node name is distinct, right? So the MPI is working correctly and it's interfacing with this. And then I can go to the OSU benchmarks. Now recall I said that the limit was 50 Gbps. How close am I getting to 50 at the application level? Okay, so I can say the same thing with bandwidth dot q sub. Now you see over here, I say 2 nodes, but only 1 process per node. So I'm putting 1 on each ping pong. I'm putting the point-to-point OSU bandwidth on that with MPI run, 2 of these nodes. And I'll say q sub, bandwidth dot q sub. When I say q stat, I see that it's running. The first job completed. You see the status column? It says C over here, right here. And here now it's saying it's running. If I run it again, it says now it's complete. So I should be able to say bw.output. And if I look at the output here, what is the peak that I see? 6295 out of megabytes per second. So megabits will be multiplied by 8. And it reached 5360. Of course, it's a 1024. But we are at 50 Gbps out of 50 Gbps. That gives a gold star to DK. So you can see the bandwidth test on something that was rated at 50, and you are reaching that limit with OSU bandwidth. For different sizes, of course, the numbers are different, but at this size, we have 6295, which translates to this 50,360. Okay, so that is pretty spectacular. So we are reaching the limits of the network using MVAPITch, and then we have built the full software stack. So if I say SPAC find -x, I have 170 packages. GROMACS, you may find 2 of those GROMACS. One is with CUDA, one is without CUDA. Okay, the same with Tau, and many versions of these packages like Trilinos. But the full software stack is available to you. You have a remote desktop. You can run graphical applications. You may have used applications like ParaView. Okay, ParaView is in your path. If I launch ParaView, there it comes up right away. I click on example visualizations. I'll choose this wavelet. And mind you, these are clusters running in US West 2. That is on the other side of the US. We are in Ohio, it's running in Oregon. Okay? In the data center of AWS, not at the University of Oregon. And you can see I can do this 3D visualization in real time. With all of you logged in, we can use 3D visualization tools like this. What did I do? I just launched ParaView, picked the wavelet example, and ran this. I can also run visit. Here is the GUI. I can click open. Here is an example.silo. It's there in the slides. I can go click add pseudo color pressure and draw the mesh by clicking this draw button. Again, here is the 3D visualization with visit, seamless across the country, running with Wi-Fi on my laptop. Let me take a slice with an operator, slicing, ISO surface, and click draw. And here is the ISO surface running on the login node. Having a remote desktop where you can visualize the results of your run right after the execution is a very powerful tool. You can use it for development. You can launch Codium, an integrated development environment. You can simply launch QSub, have 20 people launched, logging into the login node, and then all of them launching to the compute nodes. And you can run all of your applications for AI, ML, generative AI, as well as all of these tools within a single environment. I've got 4 clusters going here. So let me just again take a little breather here and make sure everyone catches up. What did I do? I first went to this URL. If you are just joining us online, please go to this tinyurl.com/E4S tut. My slides are over there. Pick a login. Go click on this paratools.adaptivecomputing.com. Give the login name, give the password. Please raise your hand if you are unable to log in. And then click that link that you see on that cluster. Open up the VNC viewer, allow pop-ups, and then you should have a terminal, a remote desktop, and then it should be able to log in. How many people here are able to log in to the for the others, are you trying and unable to log in, or are you just happy to watch? Because there's a difference between those two. If you're having some technical problems, please raise your hand if you're having a technical problem, and I'll rush right over. And I hope people online are able to connect just as well as people who are sitting here. We want to make sure that this experience is the same whether you are joining us from a remote location or whether you are right here. Yes? You are not able to connect? Have successfully logged in and got 50 Gbps, and I'm going 1,000 miles an hour. Well, that's why I'm going back here for everyone to catch up. So please, all the things I'm showing in this tutorial are there in the slides, step by step by step. So please log in over here. Try a different browser if you are having problems. I hope if you are on a VPN, sometimes VPNs can restrict whether you can go to a website. Maybe stop that VPN and try it. Although we have tried it with 2-3 different VPNs and it works. So,
yeah, might be Nat, you want to unmute some people who are having difficulties? They can directly ask questions.
Yes, please feel free to ask questions if you are having a problem and you are joining in from a remote location.
Yep, if anyone would like to speak, you're welcome to request to unmute.
Dr. Shende.
Yes?
I have a question about these cloud instances. So
Yes?
are we sharing G4DNA X large with everyone, or?
So, you know, what I've done is I've launched 4 clusters on AWS and 1 cluster on Google. The login IDs from 1 to 20 are on AWS 1, 20 to 40 are on another, 40 to 60, 60 to 80 on the 4th. So you can pick any other login ID from 1 to 80 and you will get on the AWS. Login IDs tutorial 81 through 100 are on the Google Cloud, so GCP, which has the same environment. So if you pick like a tutorial 86, you would end up seeing the Google GCP cluster. Feel free to pick one or more. There is plenty of space. We have a lot more logins than the people here and online. I see some questions. I'm not able to connect. I'm taken to a Google Doc. Yes, that's the intent. And Machias, you should be able to reserve a tutorial login name and then connect to this paratools.adaptivecomputing.com. Please remember like Aaron mentioned, that there is a exclamation at the end of the password. If you forget to put that exclamation, the password will not work. I am deliberately not showing the password here as sessions are being recorded, but does that help you, Matthias? If you have a VPN, please turn off the VPN and try again. Pick a different browser if you need. Just make sure that you can allow pop-ups. But is it fair to say that you are able to download the slides? Is it fair to say that you are able to see step-by-step output from the packages that I'm showing over here? And that you are able to go and run? Please go ahead. If I'm stopping here, please go ahead and try some examples. Yes?
So how do I change the MPI here? Like if I want to use...
So if you wanted to use a container, you'll have to build a container, and then you would add packages to the container using E4S ALC, and then you would use the E4S CL tool to replace the MPI. If you wanted to do that, all you have to do is go to examples containers directory and cd to the first E4S ALC and then E4S CL example, and there's just a /run.sh. You just do a /run.sh, it takes 2 minutes, it will build a container for you. You go to the other directory, you say /run.sh, it will build the application, it will substitute the MPI using MPI in the container, and it will substitute it with mvapitch. Okay, so then you will be able to run it. It's there in the instructions. If you just see the slides towards the end, you will see that example. And Matthias, you got in, thanks, perfect. Is there anyone online who was unable to log in to these cloud instances? Not hearing I should say that all of you who wanted to log in are able to log in. Is that accurate? And you are all able to run these GUI tools, even though we have like 15 people on a single node, and you are all using these GUI tools. I'll just have a request. After your graphics intensive tool like ParaView or Visit is launched and you have done whatever you wanted to do with it, just go to File and exit from it so that it frees up the memory and doesn't keep it around, whether it's a web browser or some other tool, so that if there are 15 people logged in on a single node, and more importantly, if you find that the response is lacking in some way, simply close your session and go to another terminal, take another tutorial login. There's plenty of spare capacity, all the way to 80 logins on AWS and 20 on Google. So we don't have 100 people over here, right? We have 15 people online and the rest over here. So we have more than twice the capacity. I don't think you will face any performance issues, but please go ahead and try these examples. What I'm going to do is I'll keep this image and all of these clusters running even through the break, and during the next few hours, I will just go into the cluster and see if there is anyone still there on a cluster. Then I'll keep it running. The moment you log off, then I'll bring the clusters down one by one. Okay. Everything that I wanted to show here is there in the slides. You can go step by step at your own pace and try the tools. I have an example here. Yes?
One non-technical question. How can I prevent the session, the no VNC session from timing out?
So if you time out, just go back to your AWS, ODDC instance like this.
Yeah, I'm able
And
to
just
log in, but is there any way to? Oh, okay.
Open VNC viewer.
Yeah.
And click on it again. It will pop up the window.
Right.
You can just kill the session like that.
No, I'm able to log in. I was just wondering if there is a way for me to like increase the timeout or send like keep alives or something like that.
If you what?
Like, so is there something I can do to prevent the session from timing out every 10 seconds or something?
From timing out.
Yeah. So like, let's say it logs me out. I can log back in, no problems there.
Click.
But it's yeah, sorry, go ahead.
So there are some utilities, Linux utilities, where you can change the timeout session. But for now, just what I suggest for everyone is when your browser says, should I save this password? Please say yes.
Okay.
Because whenever you get logged out, you can simply click the send credentials and it will send it instantaneously. Okay. So here are one of the things that that you may have noticed is that we have in this image the NVIDIA NeMo.
Yeah.
NeMo is to build custom generative AI. Okay. If you go to AWS Marketplace and you try to search for NeMo, you get ParaTools Pro for E4S as the first hit, and second and third. There's some firewall, and then there's AI Enterprise, which, by the way, provides NeMo in a container. ParaTools Pro for E4S provides it on bare metal. There's a huge difference between trying to do that. So what that means is, if I were trying to run a job, say EX1.
So how do you get these on the marketplace? Do you need to work with AWS for that, or is there some fees with? So how do you get the E4S software on the AWS marketplace?
There is just a process for that. I can share with that offline. I think you also have an image on the marketplace already. So the listing is not, it's a trivial thing.
Okay.
You just submit an image and it goes through security checks and then it gets there.
Okay.
But the difference here is that we have NeMo running directly for training and inferencing on bare metal using multiple nodes. Okay. And what that means is, if you launched say Jupyter notebook like this, Jupyter notebook, you get a session directly over here. If I say new Python notebook, okay, here is a Python notebook. I can say import NeMo, shift enter, and this cell is running. It imported it. I could say import, say PyTorch, say torch.cuda.getArchList, and hit shift enter, and it's running. It will show me the architectures that PyTorch supports. In this image, it's SM70, 75, 80, 86, 90. So H100 instances on AWS can use this image, and you can have import NeMo running directly. And we are using MVAP-pitch for launching NeMo workloads on multiple nodes using GPUs and the EFA. So we can do distributed training as well as inferencing using NVIDIA NeMo, whereas the NVIDIA's own container, the NVIDIA NeMo container, that uses a container. Whereas in this case, you can have a very simple workflow where you didn't have to pull out NeMo from a container. You could just say import NeMo, import PyTorch or any of your packages, and do have a remote desktop where you can run all your graphical packages and you can launch jobs on compute nodes. How many of you were able to run the OSU benchmark? All of you. So you ran a job on 2 nodes. Let's try this with PETC. An example that, yeah, go ahead.
I'm facing an error with the Julia MPI.
Jupyter?
No, Julia MPI.
What API?
Julia MPI.
Julia MPI.
Yeah.
Oh, let me just go over here. If I go to examples, first of all, remove any SPAC related things from your environment. Open a new terminal, go to Julia, examples.
I think Julia MPI or something like that. All small.
Here, Julia.
Yeah. So, could you please try Hello World? I think it was giving me an error saying like package MPI not found, and it asked me to import something. I was just wondering if my session was messed up.
Samples, Julia. This is a slightly different example. Let me just look at this offline with you.
Sure, thank you.
I had not. We do have Julia over here, as you can see.
Yep.
And I have some other set of examples that I can see later. But let me just go to, say, PETC CUDA. If I go to, say, compile.sh, I'll build PETC, this example with Parmetes and all of these libraries with CUDA over here. And you can see that I have created an executable. If I look at the star.qsub file, here is the example. I can say qsub star.qsub like this, and it will run this job with CUDA, and it is now queued like that. We have support for the tau performance system here, and I'll be showing some examples with that as well. If I wanted to okay, so here is the VNC. We set up a terminal. We go and run the bandwidth. Everyone is here with me so far? Next, you can look at the output of the MPI proc name. You can go to PyTorch directory. You can launch, say, Python f2.py. It will run this PyTorch example on the GPU. You can see the output that shows you the NVIDIA GPU. If you say Codium f2.py, it will launch this integrated development environment, the Codium, and you can see your syntax highlighted code like this. This is another important reason why you need to have a common file system where you can run GUI tools, where you can look at your source code, where you can develop your applications using MPI, and then you can launch them onto a cluster running on AWS or Google or Oracle or Azure. So you'll find that the same image with the same environment works across different cloud providers in the same way like you just logged in. Feel free to jump onto the Google Cloud, which is with tutorial 81 through 100. Just reserve a tutorial name so nobody picks the same thing, and just run the exact same environment over there, right? So with this Codium, you should be able to launch this. The next, I showed Jupyter Notebook. Here is an example, a canned plot of matplotlib, where I can go to this Jupyter Notebook, say Jupyter Notebook ampersand, cut and paste this, or even load this txt file, cut and paste and put over there. Just remember, when you copy and paste, you should use shift return in Jupyter Notebook for that cell to compute. Instead of just return, hit the shift return in the cell and it will go into like a star as the output. Anyone over here able to run Jupyter Notebooks over? Here is the example, CD examples, Jupyter Notebook, and type Jupyter Notebook ampersand. They are very commonly used in Python development activities. Aaron says he submitted 2 jobs with QSub. Excellent. I can successfully run Jupyter Notebook and plot a line graph. You will see that all the packages that are installed are accessible through the same interface. Now, this is all good if you have the packages and need the packages that are installed here. What happens when you want to pick a different package which is not available? Okay, and to do that, we will use SPAC. You can say SPAC find -x, it will launch. I showed you the visit tool already. Please feel free to use the visit tool, just look at the slides. Here is information about using chained E4S with SPAC. Let's say there is a tool that you want which is not in the image. Here is an example, Valgrind. Valgrind is not part of the E4S image. If I say SPAC find Valgrind, it will give me an error. Okay, or say it's not there. If I say which Valgrind, it's not there. You can simply say SPAC install Valgrind. Now, if you are using a departmental cluster where your sysadmin has installed SPAC in a central directory and you did this, you know what would happen normally, right? You would get an error message saying, you don't have permission to write in the central directory, right? Because that's on a read-only file system that's mounted everywhere. In this case, Valgrind will install in your home directory. It will use dependencies from the central directory, but it will install Valgrind in your own directory. And this directory is your home directory, which is mounted across compute nodes. So when you run a job, that job runs on multiple nodes, and it can access the installation, which is this SPAC install Valgrind. It even creates a module for you. So you can say module load Valgrind. That step is not shown here. I should add that. You could say module load Valgrind, and then you can run Valgrind --help. So please try this. Also try if you don't have a Python package that you need. Let's say you want to build websites and you want to use the Django tool, which is not part of the installation. If you said, Python import Django, or you looked at Django admin, which is not there, it will give you an error. But you can just say pip install Django. This requires a capital D here. And then Python or Django admin are installed. What I'm trying to get at is that this is the goal of the project, to reach the 95% mark, not the 100% mark. Because if you try to reach a 100% mark for everyone, you will fail, right? So can we create a distribution which targets that 95% of all the packages that you need? And then the remaining 5% you can customize yourself in your own home directories in a multi-user environment. That is very important. We have 2 compute nodes, but we have 20 people logged in on the login node, and each user can customize their own environment while being on a cloud system. This is very similar to spinning up a cloud cluster that resembles your HPC data center based environment where you already run QSub based jobs, right? And I will do this here. I'll connect to my instance. And I'm saying, okay, let me just see this job, which I first ran, qstat. And I can see the bench ksp_sol.output. You can see it ran my job with PETC on the GPU. If I wanted to measure the performance of this job, I could just look at this qsub, and then I can add here spac load tau plus CUDA and say tau exec dash t kubT MPI with kubT and event-based sampling. This is in the slides again. I added this tau exec command with event-based sampling and CUDA profiling tools interface. And I can submit a job like this and generate performance data with tau. Here are some exercises with tau. We are short on time. I cannot go into every one of these, but I can just show this. And you can see over here, I have tau plus CUDA. I can specify this. Even a profile format as merged, and then run it, and then I get a tau profile.xml, and I can generate the data.
Does this help us find out, let's say, things like the amount of time it takes to move the data from CPU to GPU, the time for which the kernel executed? If you don't mind, can you show how that
absolutely.
looks like?
So here, for example, again, just to be consistent over here, I can say export tau profile format equals merged, and then qsub star.qsub. So I have submitted 2 jobs here, and one of them is completed, one of them is queued. Here are the profile files. So you can see over here is the thread statistics table that shows you all the PETC timers over here. Even shows you the time spent in MPI collective operations where it was stuck in a barrier. This is MPI collective sync time. It will show you the time spent in CUDA calls. It will show you internal PETC timers, and the thread 1. Here we see this is not doing anything significant. Thread 2. Here, memory copy, host to device, device to host. You can see the kernels running on the GPU. Here is a QSparse kernel that ran on the GPU. And you can see the time it spent over here. And you can look at detailed information about the time it takes for memory copy from host to device and device to host over here. These are other context synchronized timings. You can also look at the time over here on thread 2 with the context event window, and you can see bytes copied from host to device, device to host, and where that data transfer takes place. So you can see how much data transfer took place from host to device and how long it took for that transfer to take place. So context events are all there. All I had to do was change this so I could use spac load tau plus CUDA, add this, and add the qsub script so that I can change this with EBS.
So with the MPI collective sync, Is there a way for us to figure out which process entered first and which process was the last one to enter?
In MPI calls?
Yeah.
Absolutely. You can generate trace files like this. You can just turn on export tau trace equals 1, and then you can use perfetto.dev to create flame graphs which show you the exact entry exit for all the ranks and generate the trace files with the GPU information.
Okay.
So that this is exactly what it looks like.
Do you have an example of
Yeah,
how this
so right here, if I just take this and just go to star.qsub, and I can just say export tau trace equals 1, okay? Like this. Here I can omit out this tau profile format because I'm generating trace files. If I say qsub star.qsub, it will now run with tracing enabled so that I'll get trace files that can be merged and converted into tau trace files which can be visualized in Perfetto. And I have a browser right here, a Firefox browser in this, so I don't have to go and transfer the files anywhere. I just launch it and visualize it. I can just look for the qstat. You can see it's running here. The previous run which generated the tau profile.xml can be seen with paraprof tau profile.xml. Sorry, I did a star. I shouldn't have. Paraprof tau profile.xml like this without the star. So here is the thread statistics table that shows you the sparse timings. These are the kernels that ran on the GPU. And this is paraprof, so it's a profile output. And if I say qstat-u, here it's completed. So I can say tau pre-merge.pl, and I have got that. And just like it says in the slide, I say tau trace to JSON, tau.trc, tau.edf -chrome, ignore atomic, and create a JSON file. Okay, so I can say tau pre-merge, tau trace to JSON, tau.trc, tau.edf -chrome -ignore atomic -o, and give it a name. Like I could say ksp.json. Okay? And then I can just launch Firefox directly from here. I don't want to set this as a default browser. Go to perfetto.dev. Perfetto.dev is a trace browser created by Google. I can click here and say, click trace viewer, open the UI, and now I'm opening the user interface for the trace visualizer, where I can then say, open trace file, and go down from the pexi CUDA directory. Here is the ksp.json file that I created. I'm clicking on this ksp.json and clicking open, and then, okay, here are the 4 ranks. I can open up this and I can click and see the contents of the trace visualization, and you can see over here, let me just close this. You can see a flame graph over here, just from this portion to that portion of the trace. If you see, you can see the main stage, step 1 vex and mat, and then the CUDA, and then the other CUDA application instances. You can say W to widen, S to shrink, and then A to go to the left, and D to go to the right, WASD. And you can see the events happening on the GPU as well as those happening on the PETC application on the CPU. So I'm just zooming in over here. I could have just as well said S to shrink or W to widen. Now, can you see all those CUDA events?
Yeah, so tau has now become a superset of, let's say, CPU-based profiling tool and something like NVIDIA's Insight. Is that?
Yes, exactly. So we have the equivalent, the timeline visualization, and I have, say, CUDA mem copy async over here. Here is the cuSparse CSRMV v3 kernel.
Okay.
You can see when it starts, when it ends. You can see for the MPI wait all, where it started, where it went, and the GPU and the CPU on one thread. There are 4 threads over here.
Okay.
I just zoomed in on the CPU-GPU combo.
Do we have the ability to intercept GDR copy calls as well? Or is it limited to CUDA calls?
So, we use the CUPT interface.
Okay.
Whatever
CUPT.
NVIDIA makes available through the CUDA profiling tools interface, we can see it all.
Okay.
The execution of the kernels, the same things that Insight uses.
Okay.
So we can generate trace files just as easily. What this provides is a development environment, ParaTools Pro for E4S, where I could launch my CUDA workloads on the login node, on the compute nodes. I could launch PETC applications with no change to the source code, build system, or the binary. I was able to dig right down to the PETC timers like this, matmult or vector scatter begin or vector scatter end. These are PETC calls from per stubs that are visible through tau. I can look at the CUDA calls. I can launch paraprof. I can launch perfetto.dev without transferring any files over at all through a web browser, so that you have a full development environment that you can use for HPC as well as AI/ML workloads. So please feel free to launch these jobs, launch the NeMo workloads. There are some examples. There's a lot more in these hands-on than I can show in this time. It says no cable connected. Can somebody in the AV? Okay, there it is. So just to show you a quick, I'm going to go through these real quick. Here's the CUPT example. There was one on T-Leaf CUDA. You can run it. You can see the kernels running on the GPU. You can say SPAC load tau plus CUDA, run this with PETC CUDA, do exactly what I did here, and launch perfetto.dev, and open up the example with the JSON file format. Here's a paraprof 3D profile browser, and you can launch this just to show you that there's 3D graphics that works properly. And then, here, let me just take a second to go to a tau directory, say paraprof demo.ppk. Did my other example complete? Here, this was the NeMo example. It looked at this file and said the contents of this file are GLENN. This is a standard NeMo example. It just shows that it ran properly.
Can you explain what that is? I also ran it and I got that output.
So there is a file. If you download this WAV file, this, and run it, it will be a person saying GLENN. They won't say Glenn, they just say like that. And so it was just transcribing that file. You can even use this API to convert from one language to another. So you could do a streaming example. This was running on the GPU using a model. And what is important is that this model, QuadsNet 15 by 55 based en.nemo, this model has an extension that ends in .nemo. There are a lot of AI/ML models out there which have the .nemo extension that can be read by the Nemo framework. And ParaTools Pro for E4S right now is one of the few, to my knowledge, the only image that has MPI integration, that has support for bare metal use of GPUs. The other enterprise AI image from NVIDIA is using containers. So if you have workloads that need such capabilities of using Nemo models, you could look at this. So here is the image. The 3D graphics can be visualized with 3D visualization. Here's a quick show of bar plot. You can see that I can run this 3D view in real time on the cluster, with each user having access to 3D graphics and being able to launch such workflows. Here's a scatter plot. You can see each rank is a unique blue dot or a red dot in this. I can explain it in the break later if you are interested. But let me just take this moment to wrap up and say that that you now have the ability to launch all these tools. His lamps, similar. If you are interested in containers, as you were asking, just go to this example and see the README file. Just run it. It will create a new container with a hyper package. It will build a hyper example, substitute MPI in the container with mVapage and run it. And you can then go to Nemo and try this example with Nemo. And you can, if you have your own AWS credentials after this tutorial is over, and you want to create and use this image, what do you need to do? You can use your own AWS credentials with ODDC. First, go to the AWS Marketplace, search for ParaTools Pro, subscribe to the node and server images. We also have a parallel cluster image. We have x86 as well as ARM. So you can use Graviton nodes. You can then go to adaptivecomputing.com and click on Start Your Free Trial. And I think it's like a month. And even this has a free trial for 31 days. And then you can request this, but remember to check this box of E4S as you fill in your name and details at Adaptive Computing. Then they'll set up an account for you. They'll help you import your AWS key and credentials in ODDC. You can then connect to the subscribed image that you just subscribed to, and then specify which node you want, how much data you want on the login node, compute nodes, which shape you want, and then you will be able to get your own cluster manager. You can click over there and say deploy that cluster, and then you will have the image just like you did when you logged in with ODDC. Okay, so you can get the full set of things that I just showed. Anybody can do that, and you can get access to the ParaTools Pro for E4S with a free trial, and even the adaptive computing folks are giving free access to the ODDC. Here are some Tau reference materials for the example that I showed. You can see this. I have a separate talk on Tau, so I'll not go into details of this. But there are some environment variables that you can set. A lot of this work goes on at the University of Oregon and at ParaTools. And this is Eugene. Please consider coming to Eugene sometime and visiting us. It's very pleasant in the spring and summer. And I would like to thank our sponsors, the Department of Energy, Department of Defense, National Science Foundation, NASA, our industry partners, CEA in France, and our partners at the University of Oregon, the Ohio State University, our mVapage team, ParaTools Inc., University of Tennessee, Knoxville, TU Dresden, Hewlett Supercomputing Center, the Exascale Computing Project, and US Department of Energy Office of Science, the PESO and STEP projects and the Small Business Innovative Research grants. And with this, I'll take any questions in the break. Let's go for the break. And thank you very much for inviting me. I hope you found this useful.